Okay, this video is going to be an introduction to computational complexity. What do we mean by computational complexity? Well, this is a way to analyze algorithms to see how well they're going to perform, and specifically how well they're going to perform as we increase the amount of data that we're using to run the algorithm on. Computational complexity allows us to determine whether algorithms are going to be feasible for a particular problem, and it allows us to compare two different algorithms that are doing the same task. So maybe one algorithm is going to perform a lot better than another one, and we'll find that out by analyzing the algorithm using computational complexity. So I like to go to the beach, and when I go to the beach I take my sand pail and my shovel and I like to move piles of sand. So I have an algorithm for doing this, and my algorithm is take a shovel full of sand, put it in my bucket, fill the bucket till it's full, and move it to its new location and repeat. So for this small pile here, it takes me about 5 minutes to move the pile. However, my husband decided he was going to have a pile of sand dumped in our yard so that I could have something to do, and I used my algorithm to move this pile of sand, and it took me 5 hours to move this pile. I was using the same algorithm. Then I came across this big pile of sand here, and I was wondering how long it's going to take to move this pile of sand. Is my algorithm that I used at the beach for moving small piles of sand going to scale to moving this large pile of sand? Well, I don't really know, but I can figure this out by using computational analysis or computational complexity to determine how long it would take for me to run this algorithm and move this pile of sand. That's sort of what computational complexity is all about. It's about how does our algorithm perform as our problem size grows. And is it still a feasible solution as our problem size grows, or do we need to improve upon it somehow? So computational complexity provides us with the tools for discussing the efficiency of an algorithm. So a useful program has to have all of the following properties. It needs to perform correctly, it needs to do what it's supposed to do. It should be written so that it's easy to understand and easily modified by someone else, but it also should perform in a reasonable amount of time using a reasonable amount of system resources. Now, system resources means the amount of CPU that it takes, the amount of memory it takes, etc. But another thing that we talk about is how much time it's going to take. If you have an algorithm that's going to take a month to run, do you think your user is going to be patient enough to sit and wait for a month for the results of your computation? Probably not. So we're going to talk mostly about time efficiency and how long things take to run. And this really correlates with how much system resources that an algorithm would need to run as well. So we want to know how the running time changes as the problem size, that is, the parameters of the input, changes in size. For example, how long does it take to do some sort of a sort on a list of size 10, 100, 1,000, or 1,000,000,000,000 elements? So the conventions that we use for talking about these things, one, we use n for the problem size, so this is the input or parameters. This is typically when I'm doing computational complexity in this class, I'm typically using a list of numbers or elements. So the length of the list would be n, that would be the problem size. T at n means the amount of time it takes to execute the algorithm for a particular problem size. So first of all, what is the running time of an algorithm? What do we mean by the running time of an algorithm? What's the exact formula that we can use to find out how much time an algorithm runs? For example, how long will it take to sort a list of size n using some sorting algorithm? One typical sorting algorithm is called a bubble sort. So to answer this question exactly, we need to know the exact code that was being used, because different implementations of the same algorithm may actually take a longer time to run. We'd need to know which interpreter we're using, because that influences the amount of time an algorithm will take to run. We need to know exactly how this interpreter works. We need to know the details of the computer hardware, because your brand new Mac computer may run way faster than my very old Dell desktop computer. So we need to know, if we're going to look at the running time of an algorithm, the details of the computer hardware. We also need to know something about the operating system. So an algorithm running on one machine isn't necessarily going to take the same amount of time as an algorithm the same algorithm implemented exactly the same way running on a different machine. So the good news is that computational complexity, we don't need to know the exact amount of time that an algorithm takes to run. Basically, we just reason about the type of, we just kind of reason about the amount of time that an algorithm is going to run. So we typically look at, or we typically describe an algorithm in terms of what kind of equation is this t at n. Is it a constant time that we would need to run? So would an algorithm run basically in the same amount of time if we had a small number of elements as it would for a large number of elements? Is the equation a linear equation? Is it quadratic? Is it exponential? So knowing what type of equation t at n is enough information to decide if an algorithm is useful, if it's going to scale with a larger input, and it will allow us to compare two different algorithms. Okay, so one way that we can figure out how much time an algorithm would take is to actually count the operations that are done within an algorithm. So we count the number of basic operations. What we mean by basic operations are assignment operations, arithmetic operations, for instance addition, subtraction, list or array access, where we say array at I, comparisons, and so forth. So let's take this very simple example here. This is a function called add bonus. What we're doing is we're taking in a list of salaries from a company, for instance, and if the person's salary, we're going through them one at a time, if the person's salary is greater than $50,000, we add this bonus that we've passed in to that salary. So the rich get richer, of course. So what we're going to do is we're going to analyze this algorithm. How long is this algorithm going to take? And the way we're going to do this is we're going to count basic operations. So in line 2 we have a basic operation, I is equal to 0. That would be one operation. In here we have a loop, and we're doing a number of things a number of times. So we're going to calculate or count the number of operations that we do here. Okay, so our problem size is the length of this salary list. So this is our n. So this is the number of values that we're operating on in this algorithm. And you can imagine that this could get very large. If I have a company that's just a startup company where I have 10 employees, n would be equal to 10, and I want to see how my algorithm is going to perform if I take it to Microsoft, where we have, I don't know how many tens of thousands of employees. How is my algorithm going to perform if my sample size increases? That's the idea of computational complexity. So I'm going to look at, in terms of n, how many operations do I need to do? Okay, so in line 3 we have two operations. So line 3, so we have one operation which is finding the length of the salary. That's one basic operation. And then we have a comparison with this value I. So that's a second operation. So in line 3 we have two operations. In line 4 we're getting the salary I, so we're getting this value, we're making a list access, and we're comparing that to the value 50,000. So this is two operations that we're doing in that line. In line 5 we have an operation where we're getting a list access, so we're getting salary at I, we're adding to, so that's an arithmetic operation, and we're adding that to just a number, so that's one operation there, and we're replacing the value in the list with this new value that we just calculated. So we have three operations in line 5. In line 6 we have an arithmetic operation, so we're adding 1 to I and we're reassigning the value of I, so we have two operations there. Whether or not you understand how many operations are happening here isn't really all that important. Okay, we just have, just get the basic idea. We're counting the number of operations that are needed in this algorithm. So next we look at, and this is important, next we look at the fact that we have a loop here. So how many times are we running this loop? So the loop is being executed n times. So that's important there. So it's being operated. I'm not very good at my drawing here with my mouse. The loop is being executed n times. We're doing this for each and every item in that salary list. So the loop is executed not n times. there's 9 operations each time through. So we calculated here that we had 9 operations each time we run this loop. So we have then 9n operations in total when we execute the loop. The operations outside the loop are these. So I is equal to 0. That's one operation. This is one operation here. We're printing done, so that's 2 operations. So our total running time for this algorithm in terms of operations is 9n plus 2. So for a salary list of length n, I'm using capital N here, I guess for consistency I should have used a small n, but for salary list of length n, we have an operation time or a running time, computational complexity time of 9n plus 2. So the 2 is the time to start up and print, the 9 is the time to look at each list element. So you'll note that these are not exact times. Okay, we're not actually timing anything here, we're just making a rough estimate, rough count. So the important conclusion is what comes from the kind of equation or the shape of this graph, and the equation is linear. So the algorithm, we say, is a linear algorithm. So the time is directly proportional to the size of the list. So luckily, we don't usually need to count all of the operations in such detail. So what we're doing is we're trying to reason about the kind of equation that comes out of a particular algorithm, or the type of equation that we would use to represent this algorithm. So we use big O notation for this. So this is a mathematical notation for talking about general categories of equations. So we've already talked about this. Tn is the time to execute, or represents the time to execute the program for some problem size or input size n. But the exact formula for this Tn is difficult, if not impossible to get. We don't want to count all of these operations. All we want is general characteristics. So we come up with some kind of general characteristic for this algorithm to represent the computational complexity. So we typically say that the running time, even though we've come up with this general idea, we usually say the running time is order n. And what this means is that T of n, the time that an algorithm takes to run, it behaves like a linear formula. The running time is order n squared means that T of n behaves like a quadratic formula, and so on. So we often pronounce, and you might hear me say this in a number of different ways, we say it order n squared, or an algorithm takes on the order of n squared time. So this is what big O notation is. So what we want to do when we find the big O of a formula, we want to come up with what is the most dominant part of an algorithm. What's the dominant part of an algorithm that's going to dominate the time that's going to be required by this algorithm that's running? So if we come up with a formula for an algorithm, something like this, where Tn is equal to 3 plus 3n plus 6n squared, what's the dominant part of this algorithm? What's going to take the most time and is going to grow the fastest as we increase this problem size? It's going to be the 6n squared. So in fact, when we reason about big O notation, we take that dominant term and we basically ignore the rest of the equation. So we just say, oh, this 6n squared is going to be the dominant part of the equation, so this is going to be a quadratic equation, or a quadratic running time. We also get rid of the coefficient. If we have some coefficient in front of the dominant term, we can safely ignore that, because 6 is going to remain 6 is going to remain 6 no matter what our input size is. So we essentially just ignore that coefficient and we drop it. Another example, if we have T at n is equal to 25n plus 6 log n plus 8, which part of this equation grows the fastest? Well, log n is actually pretty fast. The 25n is going to be the dominant term. So this is the term that we're going to use to specify the big O of this algorithm. And we're going to forget about the coefficient, leaving us with an estimate of order n time for this algorithm to run. Another example, if we have this equation, the dominant term here, what's going to grow fastest is this 2 to the n term. Okay, this is going to grow faster than n squared. Even though we have a very large coefficient here, this 2n is going to be our dominant term. It's going to grow the fastest. We drop the coefficient and we end up with order 2n, 2 to the n time for this algorithm. So what we're really interested in is the shape of the curve for large n in big O notation.